Hello everyone, welcome to another video where we'll be trying to solve questions from Griffith. Okay, so here an example from Griffith. Find the capacitance. We had solved electrostatic questions, electrostatics involving electric field, electric potential. I think potential energy also, potential energy, and then work done also. So these questions we have done so far. So this chapter is basically capacitance, okay, conductors, capacitance. Okay, so, so find the capacitance of two mm, uh, concentric spherical metal cells of radio A and B. Concentric spherical metal cells. It's like this: A, B. Okay, means what? Same center or common center. Okay. Okay. So what should I do? So see, here's a thing. So if we place a charge on plus q on the inner one, so whatever the charge on the outer one, it will be minus q. Okay, the induced charge will be minus q, so that the whole thing remains neutral. Okay, because it was neutral in the beginning. So if I put a plus q here in the inner sphere, the outer sphere it will be minus q. All right. We know the field between the spheres will be what? At a distance r, field will be 1 by 4 pi epsilon. For example, there is a point here. So the whatever the field, if the distance is r, 1 by 4 pi epsilon naught q by r square r cap. This is the electric field. So potential difference between them will be what? Potential difference. What we need? We need capacitance. Capacitance C is equal to Q into V. Okay. So. My bad. Q by V. Okay. So potential difference. We have charge Q. If we can have potential difference, so what is this? Difference. So V is equal to what? Minus E dot dl. Minus E dot dl. And what? What is the capacitance of two spherical radius R, A and B? So we need to find the potential between these two, A to B. Alright? Yeah? No. Here B to A, okay? So B to A. Okay? B to A. So minus Q by 4 pi epsilon naught B to A 1 by R square dr. Okay? This is 1 by R square with dr. Alright? So now if you take the integration, minus Q by 4 pi epsilon naught uh, minus 1 by R B to A. Yeah? So minus Q by 4 pi epsilon naught minus 1 by A plus 1 by B. Yeah? So minus Q by 4 pi epsilon naught 1 by B minus 1 by A. So if I take the minus inside, Q by 4 pi epsilon naught 1 by A minus 1 by B. Yeah? Alright? 1 by A minus 1 by B. So this is a potential. Okay. Now we know what? We need the capacitance. Capacitance C is equal to Q by V. Q by 4 pi epsilon naught 1 by A minus 1 by B. So 4 pi epsilon naught. Okay, this is the answer. Or if you can simplify it a bit more, C is equal to 4 pi epsilon naught 1 by A minus 1 by B. If I take the LCM, 4 pi epsilon naught AB, this will be B minus A. Okay, so 4 pi epsilon naught AB by B minus. Yeah. Okay. So 4 pi epsilon naught AB by B minus. Next question. So this was the answer for capacitance for what? Capacitance for two concentric spherical cells. Yeah. Next question. Find the capacitance per unit length of two coaxial metal cylindrical tubes, okay, of radii A and B. So this one you try first. The length of it will be L. Okay, radius, inner radius is A, outer radius is B. Hmm. Potential difference between the what? Cylinders. We need to find out for potential difference. Again, the process will be, so well, find capacitance. First thing is we need to sort out what charges are which on which surface what charge is there. Inner surface what charge, outer surface what charge. Then we need to calculate the potential difference between the two surfaces. Okay, so then only we can calculate capacitance. It's not like a direct process. Okay, so if you see the inner on the inner surface, the charge will be, for example, charge is q. Charge is q in the inner surface. So we know again what E dot ds is equal to q enclosed by epsilon naught. Yeah. So E into ds is 2 pi s 2 pi sl. Okay. S for example s is your here your otherwise 2 pi rl, no problem. 2 pi rl is equal to q enclosed by epsilon naught. Q enclosed is q by epsilon naught. Okay. So E is equal to 1 by 2 pi epsilon naught um, q by rl. Okay, so this is a related field. How to calculate the potential? Potential is simply minus A to B E dot dl. Yeah. So B is equal to minus A to B. What is the electric field? Is equal to minus B to A to B. Electric field is 1 by 2 pi epsilon naught Q by RL. 1 by 2 pi epsilon naught Q by RL into um, DL, right? Yeah, into DL. So this one will be actually dr. Okay. See, because L is a constant length of the cylinder. Okay. What is variable? Variable is the Gaussian surface. Okay. Yeah, variable is always the Gaussian surface is the variable. So for Gaussian surface, it will take r is the distance. Okay. Minus 8. Okay. We will take all the constants out. 2 pi epsilon naught L Q. So what is there inside? A to B 1 by r dr. So if you see minus q by 2 pi epsilon naught L ln r A to B, so minus q by 2 pi epsilon naught L ln B by N. Okay, ln B by N. Yeah. So this is a what? This is a potential difference VB minus VN. When I am writing VB minus VN, the limit will be from A to B. Okay, and with a minus sign. Hmm. Ln B by N. So this is a potential difference. So if I write VM minus VB, that will be what? Just the opposite. The sign will change. Q by 2 pi epsilon naught L ln B by N. Okay. So what is the capacitance? C is equal to Q by V. So C is equal to Q by V is equal to Q by Q by 2 pi epsilon naught L ln B by. So the answer will be 2 pi epsilon naught L by ln B by. Yeah, that is the capacitance formula for what? For cylindrical surface, like concentric cylinders. Right? What is the question? Metal coaxial metal cylindrical tips. Capacitance for coaxial metal cylindrical tubes. Is that all right? Capacitance for coaxial metal cylindrical tubes. Okay. Next question. Suppose the plates of a parallel plate capacitor move closer together. Hmm. Parallel plate capacitor move closer together now by an infinitesimal distance epsilon. The result of the as a result of the mutual attraction. Okay. They are attracting each other. Okay. To express the amount of work by hydrostatic force in terms of E work in terms of E and A. And yeah, let's express energy lost by the field in this process. Hmm. And yeah, let's okay. Let's see. So Warden is actually what we know. Warden is force into distance. As they're attracting each other, their like work is done like, hmm. And the distance is what? Distance is a epsilon. Hmm. Distance is a epsilon. Force I can write pressure into area, isn't it? Because pressure is a force by area. We know the expression of pressure. We know the expression of pressure, right? So from that I can write half epsilon naught E square A into epsilon. That's it. Hmm. Isn't that clear? So this is the final expression for London. See how easy it is. Just need to remember the formulas. Right? Just need to remember the formulas. You can solve everything. Now you can actually have pressure into area into distance. That then energy lost by the field in this process. Okay, energy lost by the field in the process. Okay, energy lost is W is equal to what? Energy per unit volume. Remember this formula: energy per unit volume due into decrease in volume. Decrease in volume. So energy per unit volume half epsilon naught E square. Decrease in volume is A epsilon. So it's the same thing. How decreases? Because this is area into distance, right? Volume means what? Simply area into distance, whatever this is, decrease or increase, whatever. So area into distance is given as epsilon. Yeah, this is the answer. Energy per unit volume is called energy density, which is the formula half epsilon E square. Yeah. Next question. Find the electric field at a height z above the center of a square sheet carrying its surface charge sigma. Okay. Electric field at a height z above the center of the square sheet A, side A, hmm, carrying uniform charge density sigma. How to solve it? First of all, you need to remember the electric field for it, okay? The electric field for it is 1 by 4 pi epsilon naught. Actually, we had calculated it. 4 lambda A z divided by z square plus a square by 4. Because we cannot again calculate the electric field here, right? Like, sorry, like this one. Z cap. This is the electric field actually where? Okay. Like the center of the square. Okay. Now what can we do? Can we do is uh, okay. No. This one. This one. Okay. Lambda can be written as I'm confused myself. What is z distance here? Carrying a uniform charge density sigma. Check your result of the limiting case. But that is the result. Finally, we're not even able to. This is the formula I remembered for like electric field at the center. No, I'm unable to solve it. I'm sorry. This is the title of the video. I was trying to solve it. Mm, no, I'm sorry. I'm unable to solve it. This is for what? This is for linear charge density. You can see lambda is there. This is for a linear charge density. But here it is what? Area charge, surface charge density here. Right. Here it is surface charge. So for that, how to calculate? Lambda is equal to sigma dA. No. No, I'm unable to solve it. You try it once, okay? Try it once at home and let me know how to solve it in the comments. Okay. So these are some of the questions we solved today. Yeah, I know, like, should be able to solve this. Sigma. Sigma dA is equal to dq. dq is lambda dl. Lambda is equal to sigma dA by dl. No. Okay, please try, okay? Please try and let me know I'm unable to solve it. This is problem number 2.41 in the Griffith third edition, okay? The older one. Yeah, please try. Okay, then that's it for this one. We'll try to solve more in the next session. Thank you.